Hello students, this is Mr. Ezra. Today we are going to talk about graphing radical functions and transformations of radical functions. A radical function is basically just a function that has a root, a square root or a cubed root or some larger root. We're going to start by looking at the parent function, f of x equals the square root of x. We're going to use our table in our calculator to get a list of possible xy's to put on a graph, and then we will connect those dots together and see what this function looks like. Okay, so first, let's get out our graphing calculators. And when you get yours out, you're probably at the home screen here. So we're going to go to y equals, and we're going to type in the function. Now remember, f of x is the same thing as y. So f of x equals is the same thing as y equals, and we're going to go to y sub 1 and type in the square root of x. Second x squared is square root, and then x button is your variable buttons right there, and that is it. Now, if we're going to graph this, you want to get a good uh, window, right? So I might start with zoom standard number 6 so that I get from -10 to +10. But you notice something about this function. It's coming out from the origin, and there's no negative x values. They're all kind of positive, right? So let's kind of focus in on this part of the graph here. We can change the window to do that. Instead of going from -10, maybe we'll go from -1. And maybe we'll go all the way up to like 16 or something like that. And that's going to be the x-axis from -1 to +16, going by a scale of 1. For the y minimum, we didn't see any negative y values, so we might go a little below the x-axis by using a y min of -1. We can take our max up to like 5 or something. Whoops. Delete that and go down here to 5. So I just want you to know that you can kind of play with the window until you get something that you like, that you can really see well. Okay, so I can kind of see what this looks like, but I need to know what points are along this graph. Well, if I haven't showed you this before, this is a great place to get a list of values. You're going to hit second, graph, and go to your table. And this is a table of XY pairs that you can graph on your picture. Now you'll notice something when you do this, if you go up far enough, is that all of the negative x values have the error message next to them. And let's talk about why that is. Remember when we have the square root of like -4, right? How do we deal with that negative? We end up with an imaginary number, right? 2i. Well, imaginary numbers are not graphed on the coordinate plane. They're not real numbers, and your calculator is not understanding them as real numbers, so they're saying, well, you can't graph this. This is not going to appear on the graph because it's imaginary. So we see that the first point we get is actually 0, 0. When you plug in an x value of 0 into this function, you get out a 0. You plug in an x value of 0, the square root of 0 is 0. No negative number is going to give us an outcome, so the starting point here is going to be 0, 0. That's the first point that we're going to get on our graph, 0, 0. Well, we can look at some other x values like 1, 1. And 1, 1 works because the square root of 1 is 1. So 1, 1 is another point on our graph. Right 1, up 1. Now, if I wanted to get a few more points, I've got this graphing calculator, and it's going to give me some decimals that I can put on my graph. Like I can do 2, 1.4 and 3, 1.7. So all I do is I come over to my graph and I do 2.1, 2, 1.4, 2, 1.4, about right here, right? And 3, 1.7, about right here. So I can kind of estimate about where those are going to be if I want to add that detail into my graph. Why do you think I chose an x value of 4 to go next? I don't really need my graphing calculator to know that the square root of 4 is 2. And the next perfect square is 9. The square root of 9 is 3. So these points are all going to be like nice, easy points that you can graph. We'll go ahead and pull this down so we can see the graph is 0, 0, 1, 1, 4, 2, and 9, 3. The next easy point to graph would be like 16, 4, and that's going to be off of our graph. We're not going to be able to add that to this graph. Now, we get our graphing calculator out, and we want to add a little detail between here. We can put a point at 5, comma 2.2 and 6, comma 2.4. We can add those dots in if we want to, if we need to. But we have enough points here to get a basic idea of the shape that if we're going to connect these dots, we're going to start here and we're going to just come out through and curve this way. There is not an arrow on the left. This is the starting point. You cannot go below 0 on the x-axis because you end up with the imaginary numbers which are not graphed on the coordinate plane. So we have our function here. This is our parent function. This is the parent function that we're going to use when we start talking about transformations. Any transformation that we apply is going to be to this function. If we shift it left, right, up, down, reflect it, stretch it, shrink it, whatever we do, this is the guy that we're doing it from. You can think of square root functions as like a rocket chute, like it's starting and it's shooting off into the sky, and it just kind of keeps going higher and higher. The next radical function we want to look at is the cubed root function. Cubed root function. We're going to do the same thing. We're going to put it in our calculator. We're going to get enough ordered pairs to get a general shape. But this time, negative numbers are okay, because you can take the cubed root of a negative number. That's okay. The cubed root of -8 is -2 because -2 to the third power is -8. We don't have the limitation of no negatives here like we do with square roots. So we get our calculator out. We're going to go back to y equals. And we'll clear this out. Instead of a square root, we'll do a cubed root. Now, I don't have a cubed root button on the main screen here. If we hit math and arrow down to number 4, or just type in the number 4, we can get a cubed root. We want the cubed root of x. Cubed root of x. So, if I want to get my regular zoom, I'll choose zoom standard, and I can see this kind of doesn't go very high or low, but it goes forever left and right. So maybe I'll change the window to go from like a y value of negative, let's say -5 to +5. Zoom in just a little bit to see on the graph what's going on there. We can see that it kind of comes up and curves up through here and then across. All right, now if we go to our table, that second graph, this time there's no error messages. This time we're going to have points left and right forever and ever. And again, as we're getting these points from our calculator, there's a reason I chose for this table -8, -1, 0, 1, and 8, because those are all perfect cubes. They're perfect cubes, so we look at those. Oops. Oopsie. All right. So we look at those, we see that when we plug in -8, we get -2. That's a point on the graph. When we plug in -1, the cubed root of -1 is -1. So that -1, comma -1 is on the graph. You see 0, 0, 1, comma 1, and 8, comma 2. And I've got those graphed here, right? -8, comma -2. By the way, this scale, I don't know if you can see the -4 down here, but it's -2, -4, +2, +4. Then -1, comma -1, 0, 0, 1, comma 1, and 8, comma 2. If I need more points to fill in, I just go to my table here and I can estimate about where -1.2 is and kind of guess where all those points are. We can fill in the gaps. You can think of a cubed root function as like a swimmer doing a freestyle swim. If any of you guys are swimmer, here's the little head and the arm. One arm's up, one arm's down. That's kind of what it's always going to look like. All right, so transformations of this function are going to come in 4 different places. And you can see I've color-coded them and given them letters. And we're going to talk about each of these places, and if there is a number or a sign in each of these places, what is that going to mean in the graph? How is it going to change the parent function? We'll start with the A in the front, okay? So when you have a number before you get to the square root, not an index, not a number inside this little part here, but a number in front, like a coefficient. Think of it like a coefficient, but it's in front, right? If that number is negative, on the graph, it's going to take that rocket chute that we saw before, and it's going to reflect it. So it's going to go down instead of up. It's going to come down, right? Instead of going up, it's going to reflect across the x-axis. One way that you can remember this reflection over the x-axis for a negative a is that if there's a negative on the outside, it escaped. Get it? X-axis reflect over the x-axis. All right, now when a is a fraction between 0 and 1, or a decimal between 0 and 1, or anything between 0 and 1, we're going to think of that as a compression on the graph. It's going to be shrunken towards the x-axis. It's not going to be quite as stretched out. And if a is this leading number here, is a number greater than 1, we're going to see on the graph that that's going to be a vertical stretch. It's going to be stretched out a bit more up and down. So we have three examples here, and using those things that we just talked about, those rules that we talked about, let's see if we can guess what they are going to be. What is the transformation from the parent function f of x equals the square root of x for number 1 here? Well, we have a negative at the front, and that is going to be a reflection over the x-axis. Negative in front is a reflection over the x-axis. Well, what if we have a number 2 up here? Well, 2 is larger than 1, so that's a stretch, a vertical stretch by a factor of 2. We have a number in front now in question 3, and a negative. The negative is a reflection. The fraction 1/3 is between 0 and 1, so that is going to be a vertical shrink by a factor of 1/3. Both a reflection over the x-axis and a vertical shrink by 1/3. The b inside the square root is another number. It's going to be before the x, right before the x. And you know, when we start talking about things under the radical and things outside the radical, one thing that might help you is things that are outside the radical are going to affect the graph up and down vertically, and things inside are going to affect left and right. And things that are underneath this radical sign, underneath this square root sign, are going to behave different than what your brain is going to want them to. Okay, inside the radical, it's the opposite of what you think. Okay, now when b is negative, when the number in front of x inside is negative, that is going to be a reflection over the y-axis. So when the negative is on the inside, you might remember that it's a reflection over the y-axis by thinking, why am I in here? Get it? Why inside? Why am I? Okay. Again, we have stretches and shrinks, but this is going to be different than what you think, opposite of what you think. A fraction in here between 0 and 1, or a decimal between 0 and 1, is going to actually turn out to be a horizontal stretch. So it's going to stretch left and right away from the y-axis. When the number b is greater than 1, it's going to end up being a horizontal shrink or a compression. So things are going to be compressed closer to the y-axis. Let's look at some examples. So here we have a negative. It's inside. When it's inside, why am I in here? It's a reflection over the y-axis. Our second example, we have the square root of 3x. All right, well, 3 is on the inside. It's a number bigger than 1, and it's different than what you expect, which means instead of being a stretch, it's going to be a compression, a horizontal shrink by 1/3. That word compression and horizontal shrink mean the same thing. So horizontal shrink by 1/3. So whatever number this is going to go under 1, and it's going to be a shrink of that magnitude. And number 3, we have a fraction of 1/4. So it's really kind of this number down here that we're looking at and saying, well, this is going to end up being a stretch by a factor of 4. Since that number is bigger than, I'm sorry, between 0 and 1, it's going to be the reciprocal is actually how it's going to stretch. It's going to have a horizontal stretch by 4. Right, again, we're inside the radical with this transformation here. We're talking about h now. It's going to be the opposite of what you think when you actually start looking at these functions. If you end up with x plus a number inside, that is going to be a horizontal shift to the left. Plus h, or plus a number, is a shift to the left. When you have minus a number inside here, when you are actually looking at the function, that is going to be a horizontal shift to the right. It's opposite of what your brain wants it to be, but that's just the way that it affects the graph. K is outside of the radical. So now we're talking about up and down, not left and right. And it is exactly the way that you think that it should be. If k is positive, it's going to be a shift up the graph. If k is negative, it's going to be a shift down the graph. So we've got some examples here where things are kind of all mixed together. F of x equals the square root of x minus 3. This minus 3 is inside. Things inside behave weird. I know it's left or right, but since it's minus 3, it's going to be a shift to the right 3. Minus 5 in question 2, square root of x minus 5, is outside of the radical. So that's up or down, and it's exactly the way that we think it should be. Minus 5 is going to be a shift down 5. And for number 3, we've got the opposite of 2, which is left 2, and up 4. Okay, so you kind of got to get used to the fact that in the parentheses, if it's plus, it's left. If it's minus, it's right. But outside, it's exactly what you think. Down is negative, up is positive. All right, going backwards, sometimes we're going to be given some text and we have to actually plug in the right things into the function. So here we have a parent function, f of x equals the square root of x. We know that it's reflected across the x-axis. So if it's escaped, it's going to be outside. That's a negative a, right? So we know we have a negative a outside. It stretches vertically. Vertically is up and down. That's outside of the radical. So that's going to be a stretched by a factor of 4. Well, outside doesn't behave weird, so that's just going to be a 4 out there. And it's going to translate up 1 unit. Well, up and down is outside. It's at the end, so it's going to be plus 1. If it's not mentioned, it's not going to be part of our final answer. Okay, so we're going to end up with f of x equals negative 4 radical x square root of x plus 1 at the end. Another example here. The parent function is stretched horizontally. Well, horizontally is left and right, and that's inside. But remember, those stretches behave weird. It's not going to be stretching by a factor of 2 is actually going to be a fraction 1/2, where that 2 is in the denominator inside. Reflected across the y-axis. Why am I in here? That means the negative has to be inside in front of b. And it's going to be translated 3 units to the left. Well, left is inside the radical, and it's always weird. It's the opposite of what it should be or what you want to think it is. So 3 units to the left is going to be plus 3. I don't see any up or down or stretches that are up and down. So I would have the square root of negative 1/2 parentheses x plus 3. My final answer there. So when we're graphing these radical functions, you can use your table to help you find some good points, but I want you to think of this h comma k here, the opposite of what's inside that's added or subtracted dx, and the what's outside as the starting point. So especially in a square root function, this is where your first point is going to be, and everything else is going to kind of come out from that starting point. We've got a few examples here that we want to graph. First, we have f of x equals the square root of x plus 6. And before we jump in, let's talk about what transformation we see here. We know the parent function starts at 0, 0 and comes out from there, but this one has a transformation. It's shifted. It's inside the parentheses, so we know that that is the opposite of what it kind of intuitively we think it should be. We're going to go left 6. So instead of starting at 0, 0, we're going to start at negative 6, 0. That's going to be our starting point, our h comma k. Our h is negative 6, the opposite of 6. And our k, there's nothing listed, there's no plus anything out there, so it is going to be 0. So negative 6, 0 is our starting point. Okay, now to get some other points on this function, we can get our graphing calculator out. We can go back to y equals and clear that out and say, well, let me find the square root of, and notice it puts a parentheses here. So we'll say x plus 6, close parentheses. So I know it's going to shift left. I know it's going to do a rocket shoot coming off to the right there. But by doing this, I can look at the graph to see, again, it's doing what I think it's going to be. It shifted left. I can go to my table. Now my errors are going to start at negative 7, right? I can't have anything to the left of negative 6 because negative 6 plugged in would give me a square root of 0, and that's okay. but I can start getting points to the right, like -6, comma 0, -5, comma 1, -4, comma 1.4. I don't have to put every single point along this. I can kind of skip ahead a little bit and do some of these nice ones. -2, comma 2. I can put on my graph -2, comma 2. I can search through here to find another good one if I don't want to put all the decimals in. Although it's okay to put these decimals in. You just have to kind of guess 0, comma 2.4 is 0, comma little less than halfway to 3, right? And then we got 3, comma 3 I see over there. So I'll put those on 3, comma 3, 1, 2, 3. And I think this is good enough. I can look for the next good pretty point and see what it's going to be. 10, comma 4, which my graph here is good enough to get to 10, comma 4, about right here. So you see as these functions kind of come out, they kind of just slowly increase. You know, they keep going up and to the right forever, but they just slowly get there. All right, we'll scroll down and look at our other example here. This is a cubed root function. Now this is the freestyle swim one. Remember, it's going to have a left and a right part. And our transformation here is that we have outside a vertical stretch of 3, which means that things are going to be a little bit higher and a little bit lower than they normally are on the parent function. We can get our graphing calculator out, go back to y equals, and get an idea of what this looks like. We'll put a 3 in first. But let me clear that out. We'll put a 3 in first. We'll hit math, cubed root of x. And then I've already got my graph at zoom standard, so I can see that freestyle swim there is coming up through 0, 0. And we don't really have a starting point with cubed root functions, but the starting point is really the middle, and it's still going to be 0, 0. If I plug in 0, the cubed root is 0, 0, and 3 times 0 is 0, so I know that point is going to be on my graph. And verify that by going to my table, second graph, and kind of searching up and down through here until I get some points. Now again, let's search for the easy points to graph. I mean, we could graph any of these decimals on our graph, that's fine, but we're going to start with -8, comma -6. 8, comma -1, 2, 3, 4, 5, 6. Right there. And then we'll -1, comma 3. Or -3. 1, 2, 3. We already know 0, comma 0. Now the other side of this is just going to be opposites kind of reflected through the origin. 1, comma 3, 1, comma 3. And we're going to have another one that's kind of the opposite of this guy on the through the origin at 8, comma 6. So 8, comma 1, 2, 3, 4, 5, 6. So you can see this is going higher because every y value along the way is multiplied by 3. We did have in the parent function -1, comma -1, but now it's -1, comma -1 times 3, which goes down to -3. So as we begin to sketch this, it would be certainly appropriate to use your calculator to get some of the decimal outcomes from, you know, like 2 comma something, 3 comma something, 4 comma something. You can get those in your graphing calculator, and you can get a pretty good estimate of where this is curving through. Once you get enough of those points where you're feeling comfortable sketching your graph, you're just going to come up and send it through the origin and then back over, and you should see that freestyle swimmer where his left arm is, or one of his arms is down and his other arm is up, and it kind of goes through the middle. Now it kind of looks in some graphs like it goes straight up and down here, but it's still a function. It doesn't. It's just it increases very fast near the origin and then kind of levels out as you go in both directions. Well, that's it for radical functions and the graphs, and you'll get plenty of practice graphing them and talking about transformations. Just remember that as you're doing this, we can show these transformations in the function itself, but they also can be shown in function notation. So in function notation, if you add something, f of x plus something, that's a shift up or down. If it's inside the x, f of x, like f of x minus h, well, That's exactly the same rule as being under the radical. It's going to be minus is going to be to the right and a plus is going to be to the left. A number in front of the function is a stretch up or down, a vertical stretch up or down, um, or a compression, vertical compression. If it's inside the parentheses, it's like being inside the radical, and that's where we get our stretches and shrinks in the horizontal direction. That's the left or right direction. Remember, a fraction between 0 and 1, or a decimal between 0 and 1 is going to be a stretch by the factor of the reciprocal of that fraction, and the numbers bigger than 1 are going to be compressions, again, by the reciprocal. So you can think of it inside the relationship of stretch, just whatever number is in there, change it to its reciprocal, and then think of it as a stretch or a shrink from there. So the reciprocal of 1/5 is 5, that's a stretch. The reciprocal of 3 is 1/3, that's a shrink or a compression. If the negative is outside, it's across the x-axis, it's escaped just like in the function being outside the radical. If it's inside the function notation, it's just like being inside the radical, and that would be why am I in here, a reflection across the y-axis. Well, that's it for today. A lot of information, I know. Now that we've finished with our graphs, we're going to talk about characteristics soon and then start solving some equations. Then we'll have another test. Things are moving along quickly in this Unit 4A. If you have questions, make sure that you ask them, and I will see you in class.